Hello, so we've completed the Strand chassis compliance, all of the tests and studies that are required that you can see down the bottom of the screen there at the moment. So VSB1, the chassis strength, we've already covered that like in another video, so I won't get too far into that at the moment. Once it all loads up, look, my computer's fairly slow with this stuff and there's a fair few studies to do, so I've cut out most of the loading sequences apart from this first one, so I can be a little bit more onto it with some of the other studies to show you. This is just an example of like how long it can take to load up some of this stuff if you don't have a super fast computer. So basically with this one, I'm just gonna show you like how I probe and get some of the top studies, or show people out there how to probe. If you've been doing, or if you are doing chassis compliance or anything like that, hopefully this helps you out a little bit if you're trying to learn like I had to. So this one here, remember in the last video we saw those forces there. We know that they're not in excess of 108 MPa. So we were able to get the safety factor that we were looking at because they were 460 grade materials. So now we can have a look at the ADR longitudinal test. So we'll load up our stress on that. So the longitudinal test is, you can see there 4200 kgf. I've used metric values for the forces. Just because I find it a little bit easier. So that's 1.2 G is the test on this one, the fixed point, or the forces being applied to the mounting bolts or the mounting location where the hitch would be, the chassis rails or fixtures. And so there you can see the results. So it came through pretty good on most of the studies. Nothing that I was concerned for. It's all documented with the final reports and stuff, which will be available on Patreon if anybody actually wants them. If not, you're welcome to get the models and stuff like that and just do the FEAs and stuff yourself, which I suggest because any of my findings will have to be concluded as well too by an engineer. But in this case, you know, it shows you, at least if you wanted to dive into building this sort of thing, then gives you the guidelines to show the forces. So here during the probe we select the faces. In the last video I did make mention that like the video card stuffs up every now and then and doesn't show these little faces. So you see like the blue lines it shows as I'm selecting the areas. That's what I was talking about, and see that just helps you keep track of which faces you have selected, haven't selected, and in this case that's really useful because we're not just testing, so we have an RHS, so we're not just testing or probing the outside of these areas. We want to try to get inside too, and luckily we've got some holes here at the front for gal alleviation and also for the loom to pop through, which lets us see inside the RHS and select these areas. And you can see there's a little problem area there at the back, but again, we've spoken about force anomalies before as well too in videos, so you know it's easier to identify force anomalies and stuff, which I'm quite confident that is due to the nature of how it builds up in such a very small area. So here we've got everything selected, and all we have to do is just update our list over here, which gives us all the values that are found there, and then we just sort it into the highest value to lowest. And you see here we get this 382 up the top there, and that's that problem location that I was talking about. But you can see here it's on 2 elements, and it's right at the location where it's meeting the fixed geometry. So I'm not concerned about that. I've put that down as a 324. The top MPa in that study is a 324 because I see the other 2, you know, even to a certain extent, the 300s and stuff are a result of the fixed geometry. You could, you know, add a little bit more give to that area to try to simulate it better, but in this case we achieved the fact that we needed to, even with the fixed geometry, so we're happy with that. If you wanted to go for really high safety factors and stuff like that on your designs, then you could constrain your model differently for your own studies. I've run multiple studies to get the conclusions that I've got. These videos will just show you highlighting some of the problem areas and stuff. I didn't do too much of the ISO clipping or anything like that in this video. Actually, none at all in this video. Mainly because it would take forever, and I know that no one's going to watch like a 2-hour video about someone FEAing a chassis. So in this case, this video, as I said before, it can just kind of help somebody. If you're out there and you're trying to figure out how to do some of this stuff, then you can watch these videos and get a little bit of an idea for yourself. So again, we're just getting rid of the excess stuff on the tabs there down the bottom. Again, we're just selecting the faces. This time we've got the transverse. So ADR62 details all of this. VSB 1 revision 6 also lists all of this stuff down in the test requirements. But for the most part, if you're looking for your test requirements and stuff, I highly suggest delving knee deep, or really it's a lot deeper than your knees, but diving right into the ADRs and get all of your information and your standards and stuff from there. I really support the ADRs and a lot of the stuff they've got there. Some of the other stuff is just like, VSB is a standard bulletin. So remember, get the information you can from the ADR. Use the bulletins to be just that, bulletins, updates on information and stuff for you to look into yourself or get a greater understanding on, mainly from the ADRs or other standards. And again, thank God we got those little loom holes at the front. So let's have a look here at the transverse. And you can see there, again, really low numbers. This chassis design could be said that it's overkill for 2.8 ATM, a 2.8 ton on the ATM. So, that one's a really clean one. We're happy to note that one down as like a 137 and didn't need any notes or specifics about, about how we got to that conclusion or notes around the higher forces found or anything like that. That was a real nice, clean study. So the transverse effect is applied at 0.5 G, just to keep that in mind. You see here now we skipped all the loading and jumped straight to the vertical test. The vertical test, you can see, I don't know if you can quite see there, but you get these tiny little force anomalies, like where it meets the fixed geometry. You can see it more there, which we'll highlight and we'll have a look at to make sure that these aren't effects that are really going to hit us badly. And again, if you wanted to get rid of that, I'll show with the vertical test on the chain later, that if you wanted to get rid of that, then you can move your fixed geometry, add more give to your fixed geometry and stuff like that. But in my case, I was just trying to get the numbers that I can. Again, if you want to maximize your safety factors, then you can go a little bit harder than that if you like in your constraining. Use pins and forces and stuff like that, resultant forces, whatever you want to do to maximize your safety factor. In this case, I was just shooting for 1. That's what we need in these cases. The studies are meant to be proof loaded, but 0.5 G to get a safety factor of 1, it helps to get a little bit more, I can say. In this case, I used 350 steels here on the front as well too. So that could have, I used 450 in the chassis rails, and then I've got 350 here on the drawbar for some reason. I don't know. I think it might have been because I thought this was a smaller van. So I thought, 350 will be fine, which it is, but I could have maximized my safety factors and stuff by going to that higher grade steel. I know that these littler vans, like this littler van off-road with a chassis like this, its main sufferer will be its carry capacity at the end of it all. I've seen it 1,000 times with these sort of off-road smaller vans. But if you've seen these FEA results and stuff like that, you'll be quite happy with what it can do. As well too, that if you were depending the suspension that you're using. If you can see the FEA results for it, if you've seen the FEA results that I put up in a video for the dust devil suspension that I intended to use to this at 2.8, it really ate that test. So you'd know then that there's a little bit of room there for give in that stuff. But ultimately, I've never really seen a lot of these vehicles fail unless it's due to poor welding or locations. There are a few out there that I've seen that are really dodgy. But look here, we've got, see these much higher forces, see 487. So in this case, this is 5, 6 elements or something, you know, that we can say where there's this massive force there as a result of the fixed geometry. So, you know, we don't want to ignore those effects too much. You know, I'll show how I got around this and everything later, that there's greater studies that can be done. But in this case, so what we'll do is I'm going to note this down as like a 320 for the safety factor. So we'll take the 320 because we can see that sort of dying down out of that red area, and that, which is a result of that fixed geometry, and it's only a little bit of force. If we had a little bit of give there, which there would be in reality, then you wouldn't see those maximum, you wouldn't see it peak out like that to the 380s or 480s or whatever it shows there. But it is something to keep in mind that you've got force on that location, especially during your design. We're going to do some bigger vans in design and everything, which is, we'll get to see all of that too. So we'll keep that in mind with those designs, and we'll see if we can add some brackets or something there at the front to get around that. So a chassis like this, on a build like this, see, the chassis itself will already be about a ton of your mass. So, you know, the chassis itself consumes a good 50% of your ATM, or in some cases, you know, up to 50% of your ATM. That's why smaller off-road vans often have to go for stuff like this, unless you're shooting at really low ATMs. Get a very different effect then. So now we're going to do the ADR chain longitudinal. And like you can just see by the FEA results that there's not much force there. And this is obviously, I don't know if you saw or not in the fixture, but the force is applied to the actual mounting point of the chain. If anybody out there is having problems with chain mounts in their FEAs, or if you're still using old just the chain welded to the chassis, or if you're doing anything like that, consider using a setup like this. I found this little chain mount here was really effective as compared to ones I've worked with in the past. And I've worked with ones, you know, people put bolts through them and have big holsters off the side and everything. This is sort of taken from like a truck one. It's the same mass, the same amount of weight and everything, well, fractionally more than you get with the bolt setup and everything. But like the results of this test here are really high. I know why people like to see the bolt, because the bolt itself can take insane yields, but the housing itself can be a real pain in the ass during FEA and trying to get your ADR results. Whereas this setup just eats it, you know, and if you put a chain on that, on the front of that, the chain will fail before that bolt does there. And it's mainly because the bolt is cut into either side. It's not just welded in between the plates. So all the force of it is then backward, you know, applied backwards to those plates and into itself as well too, to bend. It's really hard. So here we see our maxes, longitudinal. You know, we got a 132. So we just ate it up, nice and easy. And you can see that I probed a lot of locations there, and really you don't have to probe that much. You know, it's about looking at where your forces are and then probing those areas and stuff like that. That's why the ISO clippings are so helpful, because it cuts away everything and lets you see the mass build up and lets you really pinpoint it out. Okay. So the chain vertical test, as I said earlier about it spanning its distance out. So here, this when I applied it the first time, it gave me this sort of result, which, you know, still showed that the exact same effect of the vertical test. You see that 382, like just up inside this RHS member, I was still getting those higher yield ranges there. And you see like here as well too, where it's meeting the rail, it's right on the point, you know, and that shows like a real bend. So, you know, I got concerned about that with this test and tried a few different things. So here you can see I took away that constraining so that the force could move more further into the rail. And in that case, it really ate it up and didn't exceed anything of, you know, 240. So that gave me a bit more faith that it was just a result of the fixed geometry. Whereas this, the final test here, which is the one I use for the results too, you can see how like there's no force applied through the rail or through anything. So, you know, how did we get that result when these other results were showing such high forces? Well, what we did is this test is asking us to test the chain mount. So we isolated a lot of the members around it, and what we did there was add some extra constraints to kind of hold the force in a little bit more. And I will show you those constraints to show you yourself, you know, how to do it yourself as well too if you had this problem, because sometimes you do get this issue with this test, even though it's only a 0.5 G. So, you know, it's something to keep in mind for people, is that a lot of force is applied to that chain if it drops off the back of your vehicle. Sometimes it's better if it actually hits the ground, bounce back up or something like that. But, you know, if the chain itself takes a full bump. But in this case, we're dealing with trailers above 2.5, so we're always going to have two chains attached, which is very helpful there. So you know that then it's not actually going to show you this force. This force here you could actually divide in two because of the, but for the nature of the test, we're just showing it like this. And there you can see 66, real good. It's a bit cheaty actually, but I've seen other chain mounts really struggle in that exact same test in the exact same conditions. Okay, so this is why I say give this chain mount a test if you've struggled in your designs with one or something that can take high forces. It's simple, it's not that much extra weight, it's just a little bit more steel, and it's so worth it. So we'll have a look at those constraints. So here in the fixed, so what I did was I added like two more constraints, and you can see there I fixed the top of the chassis rail and I fixed the bottom of the chassis rail as well too. So as I said, it's a little bit cheaty because in a way what it's done, you know, is it's isolated the force all into that area there, but we can see that the structure in that area there holds that force extremely well within that distance. In our case, we were just trying to test the chain mount. Our vertical test has been done elsewhere in our previous tests, so that was all that we actually needed. Yeah, so, you know, if you wanted to go try build one of these or something, you know that you've got full compliance there. I've got results for it and stuff if anybody wants it. You know, and this is important too, just to show you here in this like for my reports and stuff, and you can see there I've got the I always supply my material properties to show you the materials intended to be used, and the loads and fixtures. I think that's really important because that will define for you the constraints that have been used in the studies, which can either help you do your own and or challenge the results, whatever. It's very helpful to have that information. I know a lot of people like to just do conclusions, and that's fine too. Trust your engineers. So the Strand's pretty much ready now, and it's going to be available. If anybody wants it, please grab it. It's going to be all the parts and everything. The full assemblies are available as well too. And that's all. Yeah.